Good morning, everyone, and welcome to the very first session of the very beginning of the NIPS conference. These are the tutorials that we're having here, if you're wondering. And I'm here to introduce our very first tutorial, which is by Professor Chandra Chakuri. Actually, it's a great honor to have him here because he's not someone who's traditionally from the NIPS community, and I think it's good for us in the machine learning community to have people who come from related areas. So Chandra is a professor in computer science from UIUC. He got his PhD at Stanford in the late 90s and then went on to spend some time at Lucent before becoming a professor at UIUC. I myself became aware of Chandra's work through some of his fundamental work on multi-commodity flows and cuts in polynomial networks, which is an area that's near and dear to my heart. But you'll find that if you go to his webpage, Chandra has worked on a plethora of amazing and difficult and interesting problems in the theoretical computer science community. And so he seems to be a real polyglot of theoretical computer science topics. And in fact, from looking further, it's basically clear that Chandra is a real pillar in that community, and so we're very, very lucky to have him here to talk about what he's going to be talking about, which is some novel aspects of graph decompositions and graph partitions based on a parameter that we know in this community as the complexity parameter of graphical models, but that is the tree width of a graph, and it's some interesting work that's very related to what we're doing here. So again, I'm very happy that he agreed to come give this tutorial. So can you all please join me in welcoming Chandra to the NIPS tutorials?
Thanks, Jeff. I want to thank Jeff and the NIPS organizing committee for inviting me. It's a great honor to be here. I think it's particularly nice that the machine learning community is very welcoming of people like me who don't know much about machine learning. But hopefully a few of the things that I say could be of use, and that's mainly my goal of this tutorial. So I'll be mostly, I don't like to stand on this podium, so I'll be kind of walking around. Hopefully that's okay. So the goals of this tutorial are to give an intuitive understanding of tree width and tree decompositions from my point of view, describe some algorithmic applications, and describe some recent developments in the structure of large tree width graphs that I've been involved with. And hopefully some of you will get interested in applying these ideas to machine learning applications. And there's a lot of engineering that needs to be done. Some of the tools are fairly theoretical and advanced, and I think there is a lot of scope for making engineering progress on using some of these tools. Okay, so the setting is going to be undirected graphs for essentially all of the talk. We all know that graphs are a very powerful modeling tool, and there are a lot of things we can do by modeling problems using graphs. Unfortunately, a lot of these things that you want to solve on graphs tend to be hard. Either they're NP hard or even worse, Sharpie hard or P-space hard sometimes. So it's a natural question that people have studied for a long time. What class of graphs are easy? And how can you leverage them in applications, these properties that may be useful to understand? And it's not a new topic. People study graphs from a variety of points of view. Sparsity is a graph have very few edges. What kind of connectivity properties does it have? Is it a planar graph? Topological properties, spectral properties? Is it an expander? What's the spectrum of the graph? And many such properties. And in this talk, we'll concern with a property of graphs that we'll roughly call decomposability. And we'll see what that is formally. So the idea of this goes back to the 70s. I think it was first studied by Rudolf Helin, and unfortunately, when I just came yesterday and opened my email, there was an announcement that Helin passed away yesterday. He was 80. He introduced the notion of Treewidth in the 70s, and the concept really took off in the graph miner work of Robertson and Seymour, which some of you might have heard about. And as Jeff said, in machine learning, the idea of tree decompositions and Treewidth is typically thought of using the notion of junction trees. So if you're familiar with junction trees, that's a similar concept, or essentially the same concept in some sense. Okay. The initial motivation for Robertson and Seymour were really this fundamental work in graph miner theory. Subsequently, the concept has found many, many algorithmic applications. And one of the messages I want to convey is that these algorithmic applications and the graph structural theory are kind of intertwined. It's hard to understand one without the other. And for this reason, sometimes the material tends to be a little bit technical, but once you get past the initial technical hurdles, there are quite a few applications. So that's worth the trouble of learning some of this. Okay, so the first part of the talk, the first 20 minutes or so, I want to give an intuitive understanding of Treewidth. The formal definition often is a little bit difficult to remember, but there's a very easy way to remember Treewidth that hopefully you will take away at the end of the tutorial. So to introduce that, let's start with a simple notion called a separator. So all graphs in this talk will be undirected. So you start with an undirected graph. A subset of the vertices shown in red is called a separator. If you remove those vertices, the graph falls apart into more than one connected component. So here we get 3 connected components. So it's a separator, right? It's a very simple notion. And we'll be interested in what are called balanced separators. What is a balanced separator? That if you remove that set of vertices, no connected component that remains is too big. So what's too big? It's not more than 2/3 the original number of vertices. So you can change that 2/3 to 3/4. It doesn't really make a difference. For concreteness, we'll say 2/3. So that's called a balanced separator. That means that you remove it, and the graph falls apart into small pieces. Small is at least a constant factorless. Okay, so we all know that trees are very easy, and one of the reasons they're easy is that every tree admits a simple balanced separator. There is a vertex such that if you remove it, it falls apart. I mean, trees have many other easy properties, but this is one of them. And you can recursively decompose a tree and do various easy operations on them. And a maybe less trivial example is the well-known planar separator theorem of Lipton and Targent from the late 70s, which says that every n-vertex planar graph has a balanced separator of size square root of n. Okay? And so what can you do with that? If you have a balanced separator, you can remove that separator. You will get some components which are not too big, right? Because it's a balanced separator. And then you can recursively decompose each of those graphs, because each of them is also a planar graph. You're using the hereditary property of planar graphs, and you get a decomposition tree. Right? So these decomposition trees have many applications. A lot of planar graph algorithms are based on this decomposition theorem. Okay, so essentially, Treewidth is closely related to this notion of recursive decomposability. So informally, the Treewidth of a graph measures something about how decomposable the graph is. Okay, and so the parameter, let's call it k. If the Treewidth of a graph is k, it basically means that it can be recursively decomposed via balanced separators of size at most k. Okay? So it's a measure that is tailored for a given graph, as opposed to the planar separator theorem, which says that every planar graph has a separator of size square root n. While if for a given graph, this measures something specific to that graph. So the Treewidth of a graph is k if you can recursively decompose it using separators of size at most k. So now I'm going to give you the formal definition, which is a little bit technical, but is useful in understanding it properly, as opposed to an informal way of thinking about it. So tree decompositions are defined as follows. So I have a graph G here. What is a tree decomposition? A tree decomposition consists of 2 things. 1, a tree, and 2, a function which maps for every node of the tree a subset of the vertices of the graph. So instead of writing it as a complicated function, for each node of the tree, I put the labels of the vertices that are associated with that node. Okay, it has to satisfy some properties, and there are 3 properties that it needs to be satisfied by these subsets, and they are natural properties. One is that every vertex of this graph has to be in at least one of these bags, they are called. Okay? At least one of these bags. So that means the union of these bags has to be the vertex set of the graph. Okay? The second important property is that if you look at any vertex of this graph and look at all the bags that contain that vertex, so C is here, C is here, C is here, they should form a subtree of the tree. Okay, a connected subtree of this tree decomposition. And the final property is that if you look at any edge of this graph, let's say CF, the 2 trees corresponding to C and F should intersect somewhere. So in particular, that means that both C and F should be in a bag of one of the nodes of the tree. Okay? So that is equivalent to saying that the red subtree corresponding to F and the green subtree corresponding to C intersect. Okay? And this is what's called a valid tree decomposition for this graph. And then the width of this tree decomposition is what is the largest size of the bag, right? So in this case, no bag is more than size 3, so the width is 3. And for historical reasons, the tree width of a graph is defined as the minimum width over all tree decompositions for G minus 1. Minus 1 is really for historical reasons. There is no reason to define it that way. They just wanted to make sure that the tree width of a tree is 1 instead of 2. Okay? So don't worry about the minus 1, but really it's among all decompositions, find the one which has the smallest width, and that's the tree width. Okay? Okay, let's see some examples. So the tree width of a tree is 1, and how do we see it? Here is a tree decomposition. I just take the same tree and add, for every edge, I add one more node along that edge, and the bags corresponding to the tree decomposition here are natural. For every vertex of the original vertex of the tree, I keep the vertex the same, the label is the same as that. For every edge, I put both endpoints of that edge in that bag corresponding to that. Okay? So it's not hard to see that it's a valid tree decomposition, and the width of this is 2, and then we take off 1, and that's, you get the tree width of a tree is 1. Okay? And the tree width of a cycle happens to be 2. So you can see it the following way. Remove this edge, you get a tree. Okay? And then you can do the same trick that every edge you put a new node, but since we initially removed an edge, this vertex C has to be put everywhere, and the width becomes 3. And then you take off 1, you get 2. Okay? So tree width of a cycle is 2. And then you can say, what other graphs have tree width 2? In fact, the tree width of a graph is 2 if and only if G is what is called a series parallel graph. These are well-known graphs. So, and they're actually a fairly rich class of graphs, and they all have tree width at most 2. So even though the tree width is 2, it captures a fairly large class of graphs, an interesting class of graphs. And if and only if, in fact, it's a characterization. And those are small tree width. On the other extreme, we have the complete graph, and the tree width of a complete graph is basically n minus 1, and you just, the trivial tree decomposition, which is put everything in one bag, is essentially the optimal tree decomposition. Okay? All right? So I want to go back. Now, I started out with separators, and then I went to this formal definition of tree width. I want to connect them back together again, that why did I say that tree width of a graph is less than or equal to k implies G can be recursively decomposed via balanced separators of size k. In fact, this characterization of tree width is approximately if and only if. That is, we will see shortly that if the tree width is less than or equal to k, it means that you can recursively decompose by a balanced separators of size k. But the converse is also true. That is that if there is any subgraph of G with no balanced separator of size k, then the tree width is basically k over some constant. So this is a useful way of thinking that tree width is really capturing how decomposable the graph is. Okay? This converse is a little bit harder to prove. In fact, in this particular form, it was proved only this year. There are other ways of thinking about it, but in this strong form that I state here, it was proved only last year, in fact 2014. Okay, so let's see this connection. So how do we see that, if the tree width is in this sense k, then you can decompose the graph using separators of size k. Okay, to understand that, let's look at the tree decomposition of width k. I want to claim that if you look at any edge of this tree and look at the bags at the end nodes of this edge, then their intersection is actually a separator of the graph. Okay, why is that? Well, look at all the nodes which are on this side of the tree and look at all the nodes which are in this side of the tree. When I say the nodes, I mean look at all the vertices of the graph G which are in some bag here and which are in some bag here. Okay. So we remove this A and F. My claim is that for any vertex which remains on this side and any vertex which remains on that side, there cannot be an edge between them in the graph, which would then show that, in fact, this is a separator. Well, if there is an edge between, say, B and, say, H, then by the properties of the tree decomposition, B and H should also be in the separator. Because B, they have to, the trees corresponding to B and H have to overlap. That means that they have to cross this edge at some point. Since they are not, that means that there cannot be an edge. So this, for every edge of the tree decomposition, the intersection of these bags is a separator. Okay? So that's not hard to see. And once you have that, I claim that what we want is easy because every edge defines a separator. So you can walk along the tree and find some edge where it breaks the graph into roughly balanced components. Okay? That's not hard to see. So if the tree width is k, then there exists a balanced separator of size k in the graph. Okay? So you can remove that. Now, tree width is a hereditary property. That is, if the tree width of a graph is at most k, then every subgraph has tree width at most k. Why is that? You take the tree decomposition for G and use the same tree decomposition essentially for its subgraph also. As the width doesn't increase. So if the tree width of a graph is k, then every subgraph has tree width at most k. So once I see that we have a balanced separator of size k, you can keep on recursively partitioning it into using separators of size k. So that's the informal definition. Now using this understanding, let's go back to some more examples. So I want to claim that the tree width of a k by k grid is roughly k basically. Don't worry about the precise constant, is it k minus 1 or k or something. I want us to understand that the tree width of a k by k grid is at least k, roughly k. Why is that? Well, to convince yourself of that, let's first convince ourselves that it's at least roughly k by saying that you can't intuitively, I mean this is not a formal proof, intuitively you can see that you cannot break up the grid into two roughly equal sized pieces by removing less than k vertices. So I mean it's a hand wavy thing, but so that means that if the tree width was k, you should be able to do it. So since we can't break it up, it means that the tree width is at least k. So that's sort of a rough intuition. And moreover, we can also show that for any planar graph, the tree width is at most square root n by, again, using Lipton and Tarjan's separator theorem, because every planar graph can be decomposed using separators of size square root n. So it must be that the tree width cannot be more than square root n. Okay. So and this is really the worst planar graph in terms of the tree width. The grids are the most complicated planar graphs as far as tree width is concerned. Okay. Now, there is a closely related graph to the grids called a wall. And why are walls interesting? Well, they're called brick wall graphs because they look like bricks laid together. The interesting thing is they look like grids, right? They sort of look like grids. And you can also show that their tree width is k. The nice thing is that they're actually degree 3. So the difference between grids and walls is degree 3, and we'll come back to why this graph is important for tree width later on. Okay? These are also interesting planar graphs. Okay, now random graphs. Okay? Suppose I take a constant degree random graph. So what is its tree width? Okay? It turns out that the constant degree random graph has very high tree width with high probability. So it's actually quite large. And how large? Recall that the tree width of a complete graph is n minus 1. In fact, a random d-regular graph for d sufficiently large turns out to have tree width close to n over 3. So random graphs can actually have very large tree width, and the reason for that is a random graph is actually an expander, and expanders don't have small separators. Okay? Now, I don't want to go into the precise definition of, let's see what an expander is. An expander is a graph where for every set S which is not too big, that means it's not more than n over 2 vertices, the number of edges going out is at least the size of the S. So it's expanding. And expanders, constant degree expanders exist, and they're a very important class of graphs. And random graphs are expanders with high probability, and these don't have small separators. They have linear size separators, and so they're complicated from a tree width point of view. Okay, so a comment about tree width and sparsity. Small tree width implies sparsity. What does it mean? That if the tree width of a graph is at most k, then the average degree cannot be more than k. But the converse is not true, as we just saw. We saw that a degree 3 graphs can have very large tree width. So sparse graphs can be complicated, as we know. But if the tree width is small, then they can't be too dense. Okay? So they are, in some sense, small tree width implies sparsity. Okay, so we have introduced this parameter. How well can we compute it? Can we compute the tree width of a graph? Can we approximate it? Can we actually find the decomposition efficiently? So it turns out that given a graph G and K, checking if the tree width of a graph is less than or equal to K is NP complete. However, if I give you a fixed K, there is a famous result of Bodlander which says that for any fixed K, there is a linear time algorithm to decide if the graph has tree width at most K. Unfortunately, the running time dependence is not simple. It's not just the running time is bad. This is completely impractical algorithm. However, there are algorithms which give you something which is not exactly the tree width, but a 5 approximation in a single exponential dependence on k, and these are somewhat practical. So, and there are many heuristics in practice which are used to compute tree decomposition small width. So if you give you a small, if you want to check if the graph has small tree width, say tree width 10, you would be able to compute a tree decomposition of width which is a little bit worse than 10 somewhat efficiently. Okay? And there are a lot of heuristic algorithms that people have developed over the years to compute small tree width decomposition. And you can also approximate it. The connection to separators is important. In fact, using the connection to separators, you can approximate tree width. And in particular, the best known algorithm for tree width is closely connected to the best known algorithm for separators. So in particular, given a graph with tree width, say k, you can compute in polynomial time a tree decomposition of width k times square root of log k. Because that is the best algorithm we know for separators, and that's what you can do. Okay? All right. So tree width has many applications, at least in theoretical algorithmic world. And well, initially it was introduced for graph theory, and it's a fundamental concept there, and a huge amount of graph theory is built around the notion of tree width. But as far as we are concerned in terms of algorithmic applications, there are many such algorithmic applications, and I want to give you a taste of these applications in the rest of the tutorial. So, so some of you have seen probably polynomial time algorithms if the tree width is fixed, for using junction trees and stuff like that. And we will see some of these applications in the rest of the tutorial. So there is a rough template for how tree width is used in algorithmic applications. So what is the template? The template is that if a graph has small tree width, then you can solve many problems using dynamic programming. Right? This is probably much more familiar to a number of you here, that if the graph is small, or you can a constant, or a little bit bigger, then you can solve many problems via dynamic programming. Maybe this is not as familiar, and I'll try to convey the sense of this. What happens if the graph has a large tree width, right? And then you get a very worse dependence on the tree width. But nevertheless, there are many applications where you can use a structure of a graph which has a large tree width to exploit it to find a way around that. Okay? So it requires this paradigm requires understanding something about what do graphs with large tree width look like? Okay? And we'll see some applications of this in the tutorial. Okay? All right. Okay, so the rest of the talk, the outline will be, the first topic will be how can you use small tree width, exploit it using dynamic programming to come up with exact algorithms for many problems. And I want to emphasize a related topic that we can use this to also address graphs which have very large tree width, like planar graphs, and get a lot of applications. So this may not be so familiar. So even though we can do dynamic programming only on small tree width graphs, we can reduce to small tree width using simple tricks and get a lot of applications. So hopefully we'll see that. And the second topic will be how do we exploit the interplay of small and large tree width for certain applications and fixed parameter tractability. And the third topic will be using large tree width directly for certain approximation algorithms and how those led to some improved understanding of the structure of graphs. So hopefully you'll see all three of these and have a reasonable picture of how to use tree width in applications. Okay, so let's do topic one. And the high-level idea is that the recursive decomposability with small width allows dynamic programming algorithms for many problems. And that's not a very hard observation. It's just that we have to see some details of that. And to illustrate that, I'm going to pick a canonical simple problem, namely the maximum weight independent set in a graph. So I have a graph, and a set of vertices is independent if there are no edges between them. And I want to find the largest independent set in a graph. Okay, or maybe a largest weight independent set if the vertices have weights. Okay, this is a hard problem. In fact, it's extremely hard from the worst case point of view. It's NP-complete, and it's even, from a theoretical point of view, in the worst case sense, it's even very hard to approximate. Okay, but there are a number of positive results. Okay, so first, we'll see quickly that it can be solved efficiently in bounded tree width graphs. Moreover, we'll also see this, that if you're given planar graphs, and in fact a much larger class of graphs, you can get an arbitrarily good approximation. Okay? And both these are based on ideas coming from tree width. So let's see the first one. This is a slide from my undergraduate algorithms course, right? That how do we solve the maximum weight independent set in a tree, right? So that's using dynamic programming, right? And that's very simple. Even though it's very simple, let me just quickly go through it because I'm going to use that sort of the idea to exploit it in bounded tree width graphs. If you take any vertex V of the tree and define TV to be the subtree rooted at that, then let me move this away. TV to be the subtree rooted at V, and define opt of V to the optimum value of a maximum weight independent set in that tree, you can easily write a recurrence relation for it and use dynamic programming. But let's take a slightly step back from it and say, why does the recurrence relation work? Well, if you take this subtree and you look at this vertex V, V is a separator for that. That means if I remove that vertex from that TV, the tree will fall apart, right? Its children will be separated. So using that, we can define two quantities. For a vertex V, define opt V1 to be the optimum value of an independent set in the subtree TV that includes the vertex V. And opt V0 to be the optimum value of the independent set, maximum weight independent set in TV that does not include V. Okay, there are two quantities you can define, and clearly opt of V is the maximum of these two. Right? Right, that's easy to see. And now we can easily write a recurrence relation for this. What is opt of V1? That is, I want to include V. If I want to include V, well, I get the weight of that, plus you look at the children of V, then I cannot include any of the children, right? Because I included V. So it is the weight of V plus the sum over the children of V, opt of U0. Okay? And this is a simple recurrence. And what about opt of V0? That is, I don't want to include V. Well, it is the sum over the children of V, opt of U. Because I don't care whether you include the child or not. That is given by opt of U. Okay? So that's a very simple recurrence relation, and you can do this bottom up. So how can you do this in a general graph? Well, if you give me a graph and a tree decomposition for it, we can do dynamic programming over the tree decomposition and compute the maximum weight independent set of the graph. And just following the same idea as the trees, if you look at a node in the tree, then that corresponds, if you look at all the vertices that appear in the subtree corresponding to that, you get a graph GT. For a node T here, let's call GT all the vertices that appear in the subtree at T. Okay? Now XT, this ACF here, can be seen to be a separator for this GT, that if I remove that ACF, the graph will fall apart. The GT will fall apart into connected components. So following the idea for using trees, we can define the following quantity. Opt TS is the value of the maximum weight independent set in this graph GT, this red nodes, among independent sets I, such that I intersection XT is exactly S. So here is an example. So I want to compute at this node T, opt T, this set A. What does it mean? That among all independent sets in this graph GT, give me the independent set value such that the intersection with this ACF is exactly A. Okay? And so I have to include A, which means, and I don't want to include C and F, because that's what the definition of this is. If I want to include A, I cannot include B, and I could choose D or E, and it turns out to be opt A, T is 2. So for every subset of this XT, I compute this quantity, and once you can recursively maintain these quantities going bottom up. And what is the running time of this algorithm? Well, how many values do I need to compute at a node of the tree decomposition? For every subset of the bag there, I have to compute a quantity, right? And there how many? The width is k, that means there are k plus 1 nodes in that bag, so I have to compute 2 to the k plus 1 values at a node, okay? So for every, so the number of quantity, the number of values I need to compute at a node in the tree is 2 to the k plus 1, where k is the width of the decomposition. So the overall running time of the algorithm will be 2 to the k plus 1 times n, where n is the number of nodes in the tree decomposition. And you can bound that using the number of nodes of the graph. It's not hard to do. So combining these things, you can get an algorithm with running time which is 2 to the k plus 1 times n. Right? I'm ignoring other terms. So it's exponential in the width, but essentially linear in the rest of the graph. So if you have small width graph, then you can essentially compute an optimal solution, right? And in fact, this is one way of seeing that for planar graphs, you can get 2 to the square root 10 times algorithms, because the tree width of a planar graph is at most square root 10. You can also do it directly with the left-hand tangent separator theorem, but this is one way of looking at it. Okay, so let me give you quickly another application. I'm not going to go through the details. Suppose you want to solve satisfiability, okay? So on the face of it, it's not a graph problem, right? So everybody knows the satisfiability, I hope, right? So I give you a formula in sat form, and I want to know, is it satisfiable or not? So even though satisfiability is not on the face of it a graph problem, we can essentially use Treewidth-based ideas to solve it as follows. So you can define a graph with respect to a formula in multiple ways. There is not one way of doing it. Let's do it in one way. So here is one way. It's called the primal graph of a formula. You can do it for many other constraint satisfaction problem also. So you have one vertex per variable, not per literal, one per variable. So there are n variables, only n vertices, right? Okay, and you connect two variables by an edge if they occur together in some clause of the formula. Okay, so this is just, you completely forget about the clauses in this construction of the graph, other than creating these edges. Okay, okay, that's one way of doing it. And okay, now let me define a different way of creating a graph. It is called the incidence graph of a formula, where it's a bipartite graph. You have one vertex per variable on one side and one vertex per clause on the other side, and you connect an edge, you put an edge between a vertex and a clause, a variable and a clause, if that clause contains that variable, either in the positive form or the negative form. So are the graphs clear? Okay, easy enough. Okay, so what one can show easily, again using dynamic programming It's a nice exercise if you want to do it, that if you look at this graph and it has small tree width, then you can check whether the formula is satisfiable or not efficiently. So what is the running time? The running time depends exponentially on the width of the tree width of this graph, but only linearly on the size of the formula. Okay? And now you can ask, I gave you two graphs. Which one is better? Right? Should you use the primal graph or should you use the incidence graph? Any thoughts? Sorry? They're both similar? Well, there is some reason to use the incidence graph. And why is that? One can show that the tree width of the incidence graph is always no more than 1 plus the tree width of the primal graph. Okay? On the other hand, the primal graph can have very large tree width, even though the incidence graph may have tree width 1. Well, why is that? You can easy to see, because what is the primal graph doing? It is creating a complete graph, a clique for every clause, right? So if you have a large clause, suppose I have a clause with 10 variables, then I will create a clique of size 10, and the width will automatically be at least of size 10, okay? Even though the graph has small tree width in the incidence graph. So the incidence graph is a more powerful representation as far as tree width is concerned than the primal graph. The primal graph ignores certain things. Okay? I mean, it can create large tree width even though the formula is not so complicated. All right? Okay. So you can do dynamic programming and you can solve SAT on these things. All right? Okay. So that's right. So and many of you might be familiar with the application of tree width to graphical models. You're probably more familiar with it than I am. So you can do inference in graphical models, either Bayesian networks or Markov random fields, if the underlying graph has small tree width. Okay? You can see it as dynamic programming, or you can use belief propagation, but essentially it boils down to dynamic programming. The reason why you can solve inference on these things is essentially because if they have small tree width, you can do it, otherwise the problems are going to be hard. Okay? Okay. So we saw several examples of why it's easy to solve problems if they have small tree width. Okay? So if that was the end of the story, then that won't be so interesting, but we'll see some other applications. But before I do that, there are many problems that can be solved if the underlying graph has small tree width. So maybe a natural question is, can every problem be solved on bounded tree width graphs? It's a quiz, right? Can any of your favorite problems be solved on bounded tree width graphs? If not, why not? Why would you think not, right? Well, there are problems that are NP-hard on trees, right? There are problems that are NP-hard on trees, so clearly they have small tree width, right? So you can't solve every problem on bounded tree width graphs, because if you can't even solve them on trees. So there are plenty of problems that are NP-hard on trees, so you can't solve them, right? So that's one reason, but there are other reasons too. So now the question is, which problems can you solve? Right? I gave you some examples, but which problems can you solve? Well, you take your problem, maybe you'll sit down and you'll say, oh, maybe I can do dynamic programming on bounded tree width graphs. For certain class of problems, that's easy to do. You look at the problem and you stare at it for half an hour and then say, the dynamic programming works, right? But so in fact, there is what is called a meta-algorithmic result. The logicians like this approach. There's something called a famous result called Purcell's theorem, which I'm not going to give the details of. What it says is that any problem which has certain logical structure admits an efficient algorithm on bounded tree width graphs. Okay? So don't worry about what's on the slide. All I'm trying to say is that there is a nice logical characterization of what problems can be solved efficiently on bounded tree width graphs. So there are examples where the logic actually helps you see that a problem can be solved on bounded tree width graphs, even though it's not so obvious to see. Okay? Well, for that, you need to learn about some of this logic stuff, but don't worry about that right now. Right? But if you're really interested in a hard problem that you can't see whether it can be solved or not, you can go and talk to your logician friend. and hopefully they'll help you, right? Can you express this in this language? Okay? So this is a meta-algorithmic result. The resulting algorithm from this is not practical, so if you actually want to do something useful with it, you have to get back to dynamic programming. But at least you'll be able to see that something can be done. Okay. So far, what have we seen, right? If the graph has small tree width, then you have an efficient algorithm for it for many problems, right? Now, maybe your graph doesn't have such a small tree width, but I want to convince you that using the ideas from small tree width graphs, you can leverage them even for a much larger class of graphs. So that is the example I'm going to give you now, and this is the maximum weight independent set in planar graphs. So we saw that it's exactly solvable in bounded tree width graphs. Can we use these ideas to solve something in a more general class of graphs, right? And for that, I will use the notion of approximation. I'm confident that many of you know what approximation is. So just, to be quick and formal, an approximation algorithm for a problem is an algorithm that is efficient. It runs in polynomial time and doesn't give an exact solution, but gives you a solution which is within some factor of the optimum. Okay? If you want to solve the maximum weight independent set, maybe I'll give you a half approximation. That means that the algorithm is going to always guarantee that it's at least going to give you half of the optimal solution for every instance. Okay? All right. So in 94, Brenda Baker gave a beautiful algorithm which showed that in planar graphs, you can get an arbitrarily good approximation for maximum weight independent set, even though it's NP hard. That means given an epsilon greater than 0, you choose epsilon. Say, let's choose epsilon to be 0.01. Then the algorithm will return a 1 minus epsilon, that means 0.99 approximation to the maximum weight independent set, and its running time is 2 to the 1 over epsilon times polynomial in n. So for any fixed epsilon, this is polynomial time. In fact, there are very efficient algorithms known. I'm not trying to give you the best algorithm. So this is the best you can hope for an NP hard problem, right? That is, it's NP hard, so you can't solve it exactly, but this will give you an arbitrarily good approximation. Okay? And how did she do it? So here is how she did it, right? So basically, given a planar graph and any parameter h, a non-negative integer parameter h, say 10, she showed that it can efficiently partition the vertex set of the planar graph into 10 pieces. Partition, it's a partition of the vertices, right? Into 10 pieces, such that if you remove any piece, the resulting graph has small tree width. See, the planar graphs can have a very large tree width, right? They have square root 10 tree width. But what she's saying is that if you give me a parameter h, say 10, you can partition the vertex set into 10 pieces, such that if you remove any piece, you choose, whatever piece you remove, the graph has small tree width. The resulting graph has very small tree width. And I'll show you the scheme. It's very simple, right, in retrospect. Here is how she does it. So let's take what's a hard graph or planar graphs in terms of tree width, a grid. So let's take h equal to 3. What do I want to do? I want to partition the graphs into 3 pieces, so that if I remove any one of them, the resulting graph has small tree width. Okay? So this is how she did it. So h is 3, so I'm going to think of it as coloring the graph. So I have red, blue, and green. Okay? So you color the outer layer red, then you color the next layer blue, then the next layer green. Then you start again, red, blue, green. Then you start again inside, right? You peel away the planar graph like an onion, right? So I only have 3 colors, right? Okay. So is the scheme clear? Of course, we have to generalize it to arbitrary planar graph, but it's not hard, right? So that's the scheme. I give you 3 colors. I give you 5 colors. You start with red, blue, green, yellow, right? And then you start red, blue, green, yellow, and so on. Okay? So the scheme is very simple. Now, what is observation? The observation is that if I take out any color, you choose a color, say red. What happens if I remove all the vertices with color red? Well, I remove the red and the red. What does the graph look like after I remove all the red vertices? Well, these 2 layers, the blue and green here, have no connection to this blue and green here because I removed the red in between, right? So the graph falls apart into multiple components that look like strips of how many colors? 2 colors, right? So I have this graph, blue and green. Again, I have blue and green, but they are not connected to each other because I removed the red in between. Okay? Now, the claim is that this strip, the blue and green, that strip graph has small tree width, has tree width 4 or 5. In fact, it's less, but okay. That's it. That's the idea. Okay. All right. So now you have this simple scheme. Here is the algorithm for the maximum weight independent set. Suppose I want to get an epsilon approximation. You choose h to be 1 over epsilon. So you want a 0.1 approximation. I choose h to be 10, right? And I color the graph, and for every h, I remove that vertex set corresponding to that color. Now, what happens if I remove one of these pieces? The graph has small tree width, and we know how to solve graphs with small tree width, right? We already know such an algorithm. So you just run your dynamic programming algorithm on the small tree width graph, and then you take the best of the solutions. Okay? So the algorithm is very simple, right? You color the graph into 10 colors. I have the property that if you remove any one of those, I get a small tree width graph, even though the original graph had a huge tree width, right? And then I try my small tree width algorithm on all of these pieces and take the best of them. Okay? And that's the algorithm, and I'm not going to analyze it. It's very simple. You know, it's either we see it or it's right. It's quite simple to prove that this gives you the right approximation, and it gives you arbitrarily good approximation, right? Okay, so the claim is that the algorithm runs in time 2 to the O of h times n. So h is 1 over epsilon, right? And the algorithm gives you 1 minus 1 over h approximation. Okay. Okay. So this simple idea has led to huge number of results on approximation schemes on planar graphs and way beyond that. Okay. Now, the ideas get much more refined and complicated if you want to do other problems. But what is the basic idea? The basic idea is that I know how to solve efficiently many problems on bounded tree width graphs. So this idea is leveraging that to take an arbitrary graph, not all graphs, but planar graphs and much larger class of graphs called H-minor free graphs, which I'm not going to define right now, and decompose it into pieces which have small tree width. Cleverly, it's not tree. I mean, the independent set is the simplest problem, so it's easy to do it. But for other problems, you have to do more sophisticated ideas. But the core idea is that you can leverage existing algorithms for bounded tree width graphs to obtain very good approximations for much larger class of graphs which have large tree width. Okay? And there are a huge number of results in this area. I'm not going to touch upon them. But I also want to say that the results were also obtained with the knowledge that we can solve problems on bounded tree width. Okay? It's also a conceptual tool, not just that somehow somebody came up with a trick. The author of the trick knew that you should be able to get to bounded tree width, and I mean that is that we can solve that. Okay, so there are a large number of problems that you can solve very efficiently. The techniques have been generalized to many other contexts and so on. Okay, so they are repeated. Okay, so the summary of this thing is that bounded tree width results can be leveraged to provide algorithms and heuristics for much larger and useful class of graphs. Okay? And I think this has potential for I don't think this idea is exploited sufficiently beyond theoretical algorithms. So hopefully some of you will think, maybe I can do something about inference in planar graphs if it has certain other properties, and not just on bounded tree width graphs. So I hope some of you will think of ideas. Okay, so the next topic I want to look at is the interplay of small and large tree width. Let me see the time. So all right, so the first topic was, if the graph has small tree width, we can do dynamic programming. And we can also leverage it for graphs which may not have small tree width, but we effectively reduce it to small tree width and do dynamic programming. Okay, what about large tree width? So what is this interplay that we want to see? So many important applications of Treewidth require some fine and deep understanding of the structure of large Treewidth graphs. And the theory of Robertson and Seymour from graph theory provides many such tools. Okay? But they're kind of hard. So over time, things have started becoming simpler and people have exploited that. But we'll see some of these tools that come from the theory of graph minors, right? So to illustrate that, I'm going to give a few examples and show you how, at a high level, these tools can be useful. Okay? Okay. So let's see some familiar problems, right? So many of you might be familiar with this problem called vertex cover. So what is a vertex cover problem? I give you a graph, and I want to find a subset of vertices that cover all the edges. Okay? So here is a graph, and here are 4 vertices. I claim they cover all the edges. That means every edge has at least one endpoint in this green set. Okay? So it's an NP-hard problem, NP-complete problem. But in fact, there is an algorithm of a particular form for this problem. It's called fixed parameter tractable. That means there's an algorithm, let's think of CS2 for simplicity, that runs in 2 to the k times polynomial in n for vertex cover and tells you whether the graph has a small vertex cover or not. So suppose you want to know, does this graph have very small vertex cover? Maybe you're only interested if the graph has small vertex cover, right? If it doesn't have a small vertex cover, who cares, right? Or alternatively, there is an easy 2 approximation for vertex cover. You find that, and you say, okay, that's very big. I don't care if the graph has very large vertex cover, right? But if the graph has small vertex cover, you really want to find it, right? Then such an algorithm is useful, right? Maybe k is small, and you can combine this with many other tricks to get a heuristic algorithm that works very well, right? So these kind of algorithms are what are useful. So vertex cover has such an algorithm. Okay, so good. So if you want to solve vertex cover, you have a nice algorithm. So let's look at another problem called feedback vertex set. So what is this? That you have a graph, and I want to find a set of vertices such that if I remove it, the graph has no cycles. Okay? So here is one vertex. If I remove it, the graph has no cycles. Right? So I want to find a subset of vertices which kill all the cycles. Okay? Okay, so it has one here, and if you have small vertex, because feedback vertex set, I can find it, right? So okay. So for even this problem, there is such an algorithm, which given k and the graph runs in time c to the k and polynomial in n and checks whether the graph has a feedback vertex set of small size. Okay? And now let me tell you a very important problem for me called the disjoint path problem. Okay? So what is this problem? I give you a graph, and I give you some pairs of vertices that I want to connect or route in the graph. So I give you a graph, and S1, T1, S2, T2, and S3, T3. And I want to know, are there paths in the graph that connect these guys? Okay? We all know how to solve this problem for k equal to 1, right? Yes or no? Yeah? If I give you one pair, do we know how to solve this problem? Yeah, sure. What if I give you 2 pairs? So I give you 2 pairs. S1 wants to connect to T1, S2 wants to connect to T2. I don't want their paths to intersect. Yeah? What would your guess be if you have not seen this before? Does it look like an easy problem or hard problem? Right? So when I ask this in my undergrad class, they'll say, yeah, let's try the following. They'll come with DFS for the first one, and then let's reverse the edges and try something, right? And they come up with nice algorithms, actually, right? Or they come with algorithms, right? So it turns out, okay, in this case, there are paths, right? You can connect them with disjoint paths, right? So what about this? Let's see. Does this have a solution? Why not, right? Can you convince me that there is no solution for this? Oh, well, you can try all possibilities because it's a small graph, right? Okay. What's a nice way of looking at the fact that this doesn't have a solution is the fact that this is a planar graph and all the vertices are on the outer face, and S1 T1 and S2 T2 have to cross. Okay, they can't cross. I mean, they have to disjoint, and they can't cross because their planarity will. Okay, okay. So this is okay. So it turns out that it is not so easy problem. That if k equal to 1, clearly it's easy. We all know how to solve it. If k equal to 2, the problem is NP complete in directed graphs. Okay. So it is really hard. I mean, in the directed graphs, you didn't really think about undirected versus directed when I thought about k equal to 1, right? But k equal to 2, it's NP complete. And Robertson and Seymour, one of the main algorithmic achievement of their graph minor theory, they showed that if k is any fixed constant, this problem in undirected graphs is efficiently solvable. Okay. So as you saw, I didn't put any constant before that, right? Because it's actually unknown. The precise dependence on k is unknown because it depends on so many deep results in graph theory that we don't even know the dependence on k. So it's purely theoretical existence algorithm. But we can solve it, right? Okay. So all these algorithms or problems are what are called fixed parameter tractable, right? That is, the running time of the algorithm depends polynomially on n, but there is some dependence on the parameter k. Now, this parameter k is different for different problems, right? For vertex cover and feedback vertex set, it is the size of the solution. For the disjoint path problem, it is the number of pairs that we want to route, right? So it depends how you parameterize depends on your application and what you want to do, okay? But did these problems, did I mention Treewidth in discussing these problems or the results? No, right? All these three problems had nothing to talk about Treewidth on the face of them, right? There was nothing obviously connecting them to Treewidth. But it turns out that Treewidth plays a very important role in all these problems and many more, actually. Okay? So why is that? So there is a high-level paradigm that applies to derive results of this form, even though they didn't really mention Treewidth anywhere in the original problem definition or the solution or the statement. So what is the generic paradigm? The generic paradigm is that if the Treewidth of the graph is small, we know how to solve these problems exactly. Right? We already saw that many problems can be solved if the Treewidth is small. But we are not interested in solving this problem on small Treewidth graphs alone. We are interested in solving it in a general graph, right? But we can do this. If the graph turns out to have small Treewidth, we can solve it efficiently. But what happens if the Treewidth of the graph is large? Right? We want to solve it also on those instances. So what can we do? How can we exploit our understanding of Treewidth? And here is where we need to use some structural understanding of what a graph looks like if it has large Treewidth. Right? Okay. So let's look at, I'm going to describe in these easy cases. Let's first look at vertex cover and feedback vertex set. Here is the algorithm. The algorithm is very, very simple. I mean, this is not the best algorithm for this problem, obviously. I'm going to illustrate something. But I want to highlight the simplicity of the algorithm and use that to show you some structural result. If the Treewidth of the graph is some function, remember, what are we trying to solve? Does the graph have a vertex cover of size k? Does the graph have a feedback vertex set of size k? Right? Okay. So the algorithm is of the following form. If the Treewidth of the graph is small, use your favorite dynamic programming algorithm to solve it, because we know we can solve it efficiently, right? Okay. And if the Treewidth of the graph is large, simply answer no. Okay. The answer is no for these two problems. If the Treewidth of the graph is large, simply answer it no. Okay. Do you believe that this algorithm is correct? If I want to convince you that this algorithm is correct, what should I do? To convince you that this algorithm is correct, I have to basically convince you that this is the right thing to do. Right? Here we are doing fine, right? Because if the Treewidth is small, we are actually solving the problem exactly, right? So hopefully that is correct, right? But what I need to show you is that if the Treewidth of the graph is large, then basically the answer to this is no. That means if I choose the G appropriately, then the vertex cover of the graph can't be small. The feedback vertex set of the graph can't be small. Okay? So how can we prove that? What does it? How do we understand the connection between the Treewidth of a graph and the size of a vertex cover? Right? So to understand this, Here is a fundamental result of Robertson and Seymour. It says that if the tree width of a graph is sufficiently large, then it has a large grid sitting inside it. Okay? So what is it saying? That if the tree width of the graph is sufficiently large, some function of k, if the tree width of the graph is greater than f of k, then the G contains a grid of size k as a minor. I didn't define what a minor is, but don't worry about that. I'm going to change that a little bit. So we know that grids have a large tree width, right? We saw that. What their result is saying, the converse. What they're saying is that if the graph has large tree width, then it does have a grid as a minor. So, okay, what is a minor? Let's not worry about that. In fact, I will show you something else which is related. In fact, what they're saying more precisely is that if the tree width of a graph is large, then it contains this graph essentially as a subgraph. So this is sitting inside the graph as a subgraph of the original graph. Okay, not quite. In fact, you can have a subdivision, which means that you have some extra vertices. If I take a graph and I put a lot of vertices along the edges of the graph, it doesn't change the tree width, right? So I can put some extra vertices, right? So this is their fundamental result, that if the graph has a large tree width, then you can actually show it by showing you a nice grid sitting in there. It's not an easy result, okay? It's a quite non-trivial result. But suppose we have this result, okay? Now I claim that you can exploit this result. Once you have it, you can exploit it. How do we do that? Let's go back to this. Let's go back to this thing and say, can we prove that this algorithm is correct, right? That if the tree width of the graph is large, then it has to have a large vertex cover. Well, how do we prove that? So I want to claim that if I have a big wall like this, then the vertex cover of that graph can't be small. Why is that? Well, look at all these edges of this wall, right? What do they form? They form a matching in the graph, right? They don't interfere with each other, right? My claim is that every one of these edges has to have at least one vertex from the vertex cover, right? Okay? Because you have to cover all those edges, right? So the size of the vertex cover in this graph has to be at least about k square if this is the size of k. Right? Because I have to have one vertex per each of this edge in my vertex cover. So what I've shown you is that if the tree width of a graph is large, by using the fact that it has a large grid or a wall, then the vertex cover also has to be large. Right? It can't be small. So then I can say, no, if the tree width is very large, then as a large grid and it has the vertex cover is at least k, so I can say no, safely. Okay? So that is one reason. And now let's look at the same thing for feedback vertex set. So if the graph has a large wall like this, then I claim that there have to be many disjoint cycles. Well, I'm showing you, right? This is one cycle, this is one cycle. Now let's skip a row and then find cycles again, and then skip a row and find cycles in, right? So if I have a k by k grid, how many cycles do I get? Well, I'll get basically roughly k square, right? Okay? Now, because they're all disjoint cycles, how do I kill all those cycles? I have to have at least one vertex from each of those cycles, right? So I can't have a small set of vertices which can kill all cycles if this is sitting in front of me. Okay? So that is how you can show that the algorithm is correct. Okay? This is not the best algorithms for these problems, by the way. This is just to show you that using a powerful tool from the structure of large Treewidth graphs, you can get a first-order algorithm for these problems. Okay? All right. So that's what I'm saying, that if you can choose this G as whatever the theorem that about the size of the grid is giving you, you can choose this F to be a function of that G. Okay? So let's not worry about the precise dependence on this. We'll come back to this later on, right? So that is really the connection between this and the grid minor. Now let me say a few words about the disjoint path disjoint path problem, right? Remember, I have I give you a graph and a few pairs, and I want to check if they're connected or not, okay? So in that case, the algorithm of Robertson and Seymour uses one very powerful idea, which has also found many applications. And that powerful idea is the following. As before, if the graph has small tree width, then we can solve it efficiently. Now the question is, what happens if the graph has a large tree width? Right? They are able to use this technique called irrelevant vertex technique. They are able to show, now this requires a huge amount of work, that if the graph has a large tree width, then there is a vertex called V called irrelevant, such that the graph admits routability for the pairs if and only if they are routable in G minus V. Okay? So they show that there is some vertex they can find efficiently, such that the pairs are routable in G if and only if they are routable in G minus V. So the vertex is really irrelevant as far as the routability of G is concerned. Routability of the given pairs is concerned. Right? Suppose you could do that, then what do? You find this. If the tree width is small, use dynamic programming. If the tree width is large, then find this vertex, remove it, and recurse on the remaining graph. Okay? Right? So the crux of the matter is, how do you prove this and how do you identify this vertex? So to do that, they take 500 pages. Okay? All right? It requires the full power of the graph miner. You may say, maybe there is a better algorithm for this fundamental problem, right? If you solve it, you'll be quite famous. So there is no other algorithmic approach known to solve this problem other than using this heavy graph miner theory. Okay? And so, what I want to convey is that, well, the ideas of tree width are fundamental to understanding this solvability of this problem, right? So there's no getting around it, at least as far as this problem is concerned. And so it kind of shows you the power of the ideas that are behind this, even though they are perhaps not very practical for some of these problems, right? So the concept is very powerful, okay? All right, so as I said, understanding some of this application requires understanding powerful tools, and that comes with some price, right? The price is that the quantitative bounds are weak and the proofs are hard and long. However, a lot of people have been trying very hard and have with a lot of success to improve this theory, right? So that it becomes more quantitative, the tools are more accessible, and you find workarounds, you prove things which are not the full machinery that you need, but are sufficient for many algorithmic applications. So there are many of such developments, and I want to tell you a little bit about some of the recent developments along this direction. Okay? So should we take a couple of minutes break, or that? Shall we take a break? Yeah? 2 minutes? Yeah? Stretch? Yeah. So in the remaining part of the talk, I want to talk about some recent developments that I've been involved with, and maybe give you a sense of where I come from and why these were useful for us and stuff, right? Okay, so Large-Treewidth for approximation, some recent results on the structure. So let me go back to this important theorem of Robertson and Seymour, right? That if the tree width is greater than some f of k, then it contains a grid of size k, right? I didn't tell you f, right? And no one asked, right? So what is this f that, what is the dependence of how big of a grid can I get depending on the size of the tree width, right? So that's an important problem. So here is the history of it. So the original proof of Robertson and Seymour, f is, let's say, just enormous, right? I don't even know the precise dependence because it's an iterated exponent of k. That means f of k is growing enormously fast, right? So they didn't really bother to quantify it, right? But very soon, after a few years, Robertson, Seymour, and Thomas showed that f of k is 2 to the k to the 5. That means, let's understand this. That means that if the tree width of the graph is 2 to the k to the 5, then it has a k by k grid. Does that make sense? Okay. And then, more recently, this k to the 5 has been improved to k square log k by Leaf and Seymour and Kawabayashi and Kobayashi, right? And I want to say this particular result that Robertson, Seymour, and Thomas also showed that if G is a planar graph, then f of k is at most 6k. So that means that, the reason why a planar graph has large tree width is because there's really a big grid sitting there. And the relationship is very tight. The size of the grid is tree width over 6, basically. So it's very, very close relationship between tree width and grids in planar graphs. While in general graphs, this has been pretty poor exponential, right? Okay, so, and one of the recent results with the Chuzhoy is that we improved this to a polynomial relationship between the tree width and the grid size. So what we're able to show now is that if the tree width of the graph is k to the 98, then there is a grid of size k. Okay? So this is the first polynomial relationship between tree width and grid minor size. Okay? So again, to reinterpret this in a slightly different way, previously if the tree width of a graph was h, the grid was of size square root log h. Okay? Now if the tree width of the graph is h, you get a grid of size h to the 1 over 98. Okay? You may say, oh, that's still pretty bad. Okay? It's something, right? So it is right, polynomial relationship, which is good. And what is the limit of this, right? How big of a grid can you get in the best case? What is the lower bound, right? So it's easy to see, as someone was asking me, if a complete graph, right, on n vertices, how big of a grid can you get? If I give you a complete graph of size n, what is its tree width? It's n, basically. How big of a grid can you put in a complete graph? Well, not more than square root n, right? Because to put a grid of size square root n, I need n vertices, basically, right? So I can't put more than a square root n grid in a complete graph of size n. So I can't go beyond basically square root of h. If the tree width is h, I cannot get a grid of size bigger than square root of h. Well, we can prove slightly better. You cannot even get a grid of size square root h over log h. But for all for all purposes, it is basically, that's the only lower bound we know, right? While we are able to now get h to the 1 over 98. This 1 over 98 has been recently improved by Chuzhoy to 1 over 42. So it is getting better. So it might slowly creep towards square root h. Okay? All right. So the improvement is not perhaps the main thing that I want to emphasize. In fact, along the way, there are many other structural results that have been developed that are actually more useful than using this directly. Okay? So the grid minor improvement is maybe it's easy to state, but there are many other technical results which are much more useful in applications, which I'm not, unfortunately, because they are somewhat technical to state and develop, I'm not going to state them precisely, but I'll be happy to answer questions or provide pointers. Okay? Okay. So there are many other results related to this that are useful directly, I think. Okay? And what are some applications? In essence, many bounds which are previously exponential become polynomial, and certain hardness results, even in fact there was a paper by in machine learning on the hardness of inference as a function of tree width, and to prove that they required a polynomial relationship between tree width and grid minor, which they didn't have. So they left it as a conditional result. If you can prove that, then we will get a hardness result. So now it is unconditional. Using this result, you can actually prove that those problems are actually hard. Right? So you also have useful results from this algorithmic structural result. Okay, so I will. So how did I get into this tree width for grid minors and stuff? I'm not a graph theorist per se. Okay, so I work in algorithms, and I will tell you why I got into it and why an application that I cared about. Okay, and what is this application? It is precisely the disjoint paths problem that I talked about. That is, I have a graph, I give you pairs, and I want to route many of these pairs. Right? Okay. Now we saw that if a k is a fixed constant, then well, the theory of Robertson and Seymour gives you an algorithm, but it's completely impractical, right? And also in practice, maybe k is not small, and you have k is huge, and it's NP-hard in this case, but you want to approximate it, right? So I give you a graph, and I give these pairs, and I say, route as many as you can, right? Maximize the number of pairs that you can route, right? So this is a very natural problem from an algorithmic point of view. How can we approximate? Well, you know, there is a standard way of trying to do approximation via linear programming relaxations, okay? So what is a linear programming relaxation for this problem? I can't solve it exactly, so I will try to find some proxy for solving it. And in this case, it turns out to be some kind of a multi-commodity flow. Okay, so I'll give you an example, but at a high level, what is it, right? So I set it up as, say, an integer program, right? You know, I have a variable xi for each pair I want to route, right? I want to maximize the number of pairs I want to route, right? Okay, ideally, I want to choose xi to be 0 or 1. 0 if it is not routed, 1 if it is routed. And, well, you know, what are the constraints? The constraints is that, you know, I want to find a path for each pair such that no vertex is in more than one pair, right? Okay, that's a hard constraint too because it's integer variables. I will relax it to be a flow, okay? So I want to find a flow from Si to Ti of xi units, and the total amount of flow going through a node is at most 1. That's a flow relaxation. And that, because it's a linear programming relaxation, I can solve efficiently. So here is an example, right? A cartoon picture because the real graph is too messy, right? So what is this relaxation really saying? Look at this pair S1, T1. I send flow on 4 paths for it, right? So point 1 along this path, point 3 along this path, point 25 along this path, point 05 along this path. So how much did I send total? Well, we add this up, right? It's not even sending it integrally. It is sending it fractionally, right? And for this guy, you know, I send it along these, flow along these things. This guy was routed for 1 unit, 0.3 and 0.7. Well, what are the constraints on this flow? That for every vertex in the graph, the total amount of flow that is being routed along that vertex is at most 1. That I can enforce. Okay? Suppose I solve this. Is this any good? Right? You can say, okay, I solved this. It's what's called a relaxation. So what does it mean, is this any good? It is good if I can take a solution for this and extract many pairs that I can route. Then that's a good heuristic, right? Okay, now the question is this any good, right? Well, it turns out that if you really want to solve this, it's not very good, as this following example shows. Okay? Take this example of a grid where S1 wants to route to T1, S2 wants to route to T2, S3 wants to route to T3. They're all crossing. How many pairs can I route in this example? I can route only 1 pair because any 2 cross, so I can only route 1 pair. But the flow thinks, I can send half for this guy. I can send half for this guy. All of them can send half, 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 half. As far as the flow is concerned, it doesn't care, right? The flow is thinking that it can route half the pairs, while integrally we can route only 1 pair. Well, so there's nothing much we can do about this problem, it seems. And so we said, okay, let's scale down our ambitions a little bit, okay? So the natural question is this the only reason why we are not able to route? That because these pairs are crossing? So there is some good reason coming from previous work that this was a bottleneck, that we don't know how to handle pairs crossing on the plane. So okay, let's relax the problem a little bit. I say, okay, what if I allow you 2 paths to use a vertex? So it's not the original problem, but that is a relaxation. Or alternatively, you can think of it as follows. If I told you that every node has capacity 2, then does it make the problem easier? Okay? So is the problem clear now that we're allowing us a little bit of relaxation? Now the same question arises. Is this any good? Is this flow relaxation any good? That is, if I give you a solution to this, can you route a lot of pairs using that? Okay? It turns out that the answer took a long time, right? The answer is really is good in the sense that the flow relaxation is actually good. That given a flow value, you can route many pairs. Okay? It's just that proving that took a lot of time, right? And why did it take a lot of time? Well, let me give you how we went about it, right? And about 10 years ago, we showed a connection between understanding that question and understanding something about the structure of large Treewidth graphs. Really, we showed an equivalence, I mean, at some high level, which I am not going to make very precise. We reduced the problem of understanding how good is that relaxation to answering the following question, which is a purely graph theoretic question. That is, what is the question? If the tree width of the graph is k, does G have a routing structure of size comparable to of size k? So the answer was not that if you can solve this, then that is good, but both directions were true. That if the answer to this was wrong, then basically that relaxation is no good. Okay? So the question is, let me tell you one simple example where this makes sense. This can be made concrete, right? Okay, here is the connection. So here is the question, right? If the tree width of the graph is k, does G have a large routing structure? Okay. Remember the theorem of Robertson, Seymour, and Thomas, right? What did they prove? That if the tree width of the graph is k and G is a planar graph, then G has a grid minor of size k over 6. Remember we said it's k over 6. So grids are good routing structures, I want to claim. Okay, why? Okay, because of this picture. Okay. So I want to claim that the grid is a good routing structure. So here is a grid, and here are the things that I want to route, right? So I want to connect this pink pair, and this blue pair, and this red pair, and this orange pair, and this green pair. Okay? And I have a large grid sitting in my graph, right? So how am I going to route? I'm going to route by taking these guys and saying, go to the grid. Okay? How do they go to the grid? Well, that's not obvious how to do it. Take them to the grid, but suppose you can take them to the grid. What does it mean by taking to the grid? I don't care where these pink guys end up on the grid. Okay? You send them as you care, as you wish to the grid, as long as you send them without interfering with each other. That's an easier problem, right? If I tell you that, look, all they have to do is get to the grid somehow. Okay? Once you reach the grid allows you to route them, basically. Okay? So my claim is that as long as these guys can reach this side of the grid, you can use the grid to connect them up with one crossing. Remember, we are allowing one crossing, right? Because we don't know what to do if we don't allow one crossing. Okay? So any way you reach the grid, I can hook them up using the grid. Everyone sees this? It's easy to see, right? Okay. So grid is a good routing structure, right? So this is how we solve the problem in planar graphs, actually. Right? Now the question happens, okay, what happens in general graphs? We want a very big routing structure. Remember, we can get a grid in a general graph too. But what is the weakness of that? If I start with a tree width of k, the routing structure I get is only k over 1 over 98 even with the new results. Right? That is too small for us. We want a routing structure of size k, almost k, which is way that you cannot use the grids for that. In planar graphs you can, but in general graphs you cannot. Okay? So what is a good routing structure in a general graph? Well, there was a very nice idea, again, fundamental results, due to Satish Rao and Shuheng Zhao in 2008, building on another wonderful paper by Satish and Umesh Vazirani and Rohit Khandekar. The idea for general graphs is you embed an expander in the graph. It turns out that expanders are good routing structures. Okay? So, is it possible to embed an expander in a general graph and use that to route? And it turns out the answer is yes. But again, that took a lot of time, and that was finally done in the breakthrough work of Julia Chuzhoy in 2011, and the subsequent work. What they showed was if the tree width of the graph is k, then there is an expander of size k over polylog k. So essentially k, if you ignore the polylog k, that can be embedded into G with some congestion too. Okay, so I'll mention what that is. Okay, so they are showing that you can put a large expander into the general graph, and the parameter that of interest is tree width of the graph. Okay, now in subsequent work with Alina, who is here, we showed that, you know, this edge congestion can be made into node congestion, which is 51. And in more recent work, this node congestion is down to 2. So if you are interested in node disjoint paths, then that is what I defined the problem as. Then this gives you that 2 crossing thing, right? That you want to allow at most 2 crossings. Okay? Okay, so what does it mean to embed an expander in a graph, right? Again, I'll show you a cartoon picture. So I want to embed a graph into H into my graph G. Right? What does it mean to embed? So you take each vertex and you associate a connected subgraph of G. So this vertex goes into this guy goes into this guy goes into this, and this guy goes into this. Okay? And then each path of each edge of the graph becomes a path in this graph. Okay? Ideally, if you want to embed it nicely, you want all these guys to be disjoint and all these paths to be disjoint. Okay? Then you have completely nicely embedded H into G. Okay? In these applications, what we are able to show is that, well, you know, these paths may intersect once. Okay? Or, you know, these 2 blue guys may intersect it a little bit. Okay? Depending on your application. Okay? So, but what is the power of the results? The power of the results is that the size of the expander that you can embed is the same essentially as the tree width. Modulo, we have to lose something, and this is not pretty when you actually ask me what they are, but the dependence on k is essentially very nice. If you have tree width k, then the expander size is k over polylog k, not k over square root k or k over something. Right? It is essentially k. Okay? So now the expander turns out to be a very good routing structure using existing results. And so once you have an expander sitting in that, you can use that to route. Right? So that is the high level picture. Okay? And what is the bottom line? What the bottom line is that if you have the relaxation, you can route many pairs. This is not, it is a theoretical result, so this is perhaps not great in terms of the dependence on k, but we know that the relaxation qualitatively is actually good. The congestion we get is 2, that means we allow 2 crossings, right, not more than 2, and the algorithm is polynomial time, and we can route a lot of pairs. Okay? So basically this solved, in fact, the motivation for understanding tree width for us came directly from this application. How good is this relaxation, right? And because of our need to get very strong parameters. So I also want to say a couple of words about why this application was useful in developing certain tools. Why is it useful? Because we didn't care about the congestion so much. Okay? Suppose you said, you allow 10 crossings. That's still interesting to us, right? So we wanted a very good quantitative parameter in the size of the expander we wanted to embed, but we didn't care how much congestion you incurred. Okay? So the application motivated a relaxation of the problem, which maybe another application would not have. So that allowed certain tools to be used, which eventually led to some improvements, even in the graph theoretic world. Okay? Okay. So that is the rough outline of the routing application that motivated this work. So I want to finish basically, maybe I'll finish a little early and we can all have some coffee, right? With one last application going back to satisfiability. I like this direction of work. It's not my work, and I don't know all the details, the fine details of the results, but I like the direction of this work from an application point of view. And it goes back to SAT. So SAT is, as we all know, a fundamental problem in theory, and also, it has many applications, right? A lot of people use SAT in verification and stuff, but the theoretician thinks it's a very hard problem, right? That's a canonical hard problem from theory, but there are SAT solvers which claim to solve, instances with millions of variables or hundreds of thousands of variables, right? So what's going on, right? So it's, I think, an important and fundamental question that people attack from many angles. Why is it the case that certain classes of SAT are easy, it seems, in practice, right? That you can solve many instances. So people try many explanations, and well, there are some easy cases of SAT, right? We saw that the bounded tree width instances are easy. If your SAT formula has bounded tree width, then they are easy, right? And there are also some other easy classes of SAT, 2-SAT, Horn-SAT, some well-understood class of easy SAT, right? But really, people don't see these kinds of instances directly, right? They're able to solve SAT instances that are coming from practice, which don't look like any of these easy instances. Maybe they have some of them have bounded tree width, but even that is not completely clear. So why is it that, that they can solve this? So you can ask maybe a second order question. You can ask the question, okay, well, we know some easy classes of SAT instances. Can you take a SAT instance and reduce it to an easy class? Okay, so what does it mean, reduce it to an easy class? And a nice definition given in the work of Ryan Williams and Carla Gomes and Bart Selman, when Williams was still an undergrad, I think, is the notion of backdoors. Okay? So a SAT formula phi has a backdoor if it has small set of variables that make it easy to solve. Okay? So in many of these practical applications of that SAT formulas coming from practice, there are certain important set of variables apparently, right? That they could be the critical set of variables that once you figure them out, then you can solve it. So there are several notions of backdoors. I'm just going to define one notion called strong backdoor. A set S is a strong backdoor if every assignment to the set S, the formula that results by assigning to that set looks easy. So what happens when I assign some, I take a subset of the variables and assign some values to them? The formula simplifies, right? A clause which has yes in that will become satisfied. And if the literal is no in that, you basically throw it away, right? So what this strong backdoor is saying that once I assign to these variables, the resulting formula is easy. Okay, what does easy mean? It depends on your set of easy instances, right? Whatever you think you can solve well, that's easy, right? Okay, so this should hold true for every assignment of A. Okay. So now there's a natural question, given phi and k, can we check if phi has a strong backdoor S such that S is small? Is it true? I mean, we can empirically also ask this question, right? Is it the case that, many of the SAT instances that are arising in practice have small backdoors? And maybe that's the reason somehow the algorithms are figuring them out, right? And once they figure out the assignment to this formula, to these important variables, then the formula becomes easy, okay? And suppose we could find such a small set of variables, then you have a nice algorithm for SAT, right? You find such a backdoor and try all possible assignments to the backdoor, and then solve the resulting SAT form. Now, obviously, you can use heuristics here too. You don't have to do the brute force thing. You can do branch and bound or other things. But the idea is that if you know that the formula is going to become easy, then you might, if there is a backdoor, then you might as well want to find it, right? Or you can check, is it the case that, the class of formulas that become easy are somehow because they have strong backdoors. So it turns out that there is some nice recent results based on Treewidth ideas, which they're still very theoretical results, they're not practical and so on. But they have been able to figure out this algorithmic question, which I thought, I liked the result, so I want to state it. So one of the things that we know that are easy is that the formula has small tree width. So what this set of authors have found is an algorithm whose running time depends only on k and t exponentially, even worse a little bit, but linearly in the formula size, to check if a formula has a strong backdoor S of size at most k, such that for any assignment, the resulting incidence graph has tree width at most t. Okay? Now, this tree width can be changed to other easy classes. So, what is the gist of this results? Right? The gist of this results is that if you think that your formula has small backdoor, then there is a theoretically efficient algorithm which will check that for you. Okay? So, if you believe your SAT formula has a strong backdoor with small size, and you want to check, find out, you run algorithms on your class of instances and check if they have small backdoors, there is a theoretically efficient algorithm to do it now. It's far from being practical, but one could try to make advances on that front. Okay? So now, why did I put it in my tutorial is because this also is based on ideas from Treewidth, grid miners, and so on and so forth. And these are theory papers. They require a lot of engineering to get them to be useful. But we can answer questions like this, the algorithmic complexity of this, using ideas from Treewidth. Okay? And there are advanced techniques. They're not easy, at least so far. But Treewidth does play a role in understanding some of these questions. Okay? So more or less, that's all I had. So maybe I finished a little earlier. Hopefully, that's not a bad thing, right? So we'll stop there and have some conclusions. I think Treewidth and tree decompositions are a powerful conceptual tool in algorithms, in many different areas of algorithms. So I hope you got a sense of the fact that having a little bit of understanding of graphs with large tree width is beneficial in attacking certain class of problems. It's not just that if the tree width is small that we can do dynamic programming. The complementary side, if the tree width of the graph is not small, then we should investigate whether we can reduce to the small tree width case, and there are many cases where you can do that. And knowing some of the tools from the structure of graphs with large tree width helps you understand that, or at least talk to a theory person and collaborate on transporting tools from this area to maybe perhaps an application in machine learning or inference or other applications. So that's so some practical successes, but I hope for more in the future. Thank you.
We have time for questions. If everyone who asks a question could please use the microphone.
Yes. Yeah.
Yes, I'm confused about the operating mechanism by which, given the flow problem, I set the capacity of the edges to 2, and then I solve the LP, and then I interpret, I round the LP somehow in order to get a solution to get me a lot of flows. Can you explain that a little bit?
Sure. Let's see. I glossed over that. So okay. So I hid all that in this slide. So what this work does is basically takes a solution to the flow problem. Okay. So you get, what do we get from that? You get these numbers, right? Okay. So using these numbers, we do some processing of the graph and cut it up into many pieces and get down to this case. Okay. Now, okay, so we effectively take the solution to the linear program, cut up the graph into many pieces, and solve the problem independently in each piece. Okay. How to do that, I am not telling you because that's a lot of details, right?
I like details.
Okay, well then we have to, I'm not sure everybody else wants to see the level of detail. It takes a bunch of work. Okay, so I don't think I can answer this in 2 minutes in an intelligible way that makes sense to everybody here. I'll be happy to talk to you offline.
Sounds great. I'd really appreciate that.
Yeah, it's a bit complicated. Yeah. So everything was clear then. Okay. I'm around, so happy to answer any questions later. Yeah.
So I have a question.
Sure.
So have you studied any generalizations of tree width to sort of weighted graphs in the sense that you can measure a graph strength by something that if the weights were all 0, 1 would essentially recover tree width, but with 0, 1, weights between 0 and 1 would be something perhaps more general. So in some sense there would be like a strong backbone in the graph where weights are greater than a certain value, or where some complexity parameter which is based on a continuous parameter as opposed to just 0, 1 valued weights. It seems like a lot of applications would potentially, especially like the routing problems and flow problems, could potentially use that.
There is a notion which I didn't cover because it's I didn't want to introduce too much notation. Tree width is closely related to separators, but there is also this notion of what is called well-linked sets. So in fact, that's a very important notion in many of these applications, but I avoided the notation. A set of nodes in a graph, actually I have slides for that. So maybe I can go quickly to that slide, though. Yeah, so I talked about separators for the entire graph, right? But there is a notion of separators for sets, not the entire graph, but just for sets. And we can say that a set is well linked or strongly linked if it cannot be broken up in the graph with small separators. Now that notion can be generalized to fractional notion. You can say, I put weights on the vertices and say it's between 0 and 1, and they say they're fractionally well linked if there is no small separator in a fractional sense for that. So in that sense, actually, there is some generalization, and that actually helps a lot in many of these applications. But I didn't define it because it's a technical tool which is used in many of these things, but there is such a notion. Yeah. So the key word to look for there is well-linked sets. A set is well-linked if you cannot break it up easily, and that you can make it fractional also, if they have weights on the vertices. Yeah.
So are there other questions? Because if not, I have another question.
Sure. Yeah.
I want to ask you again about the first question, but I'll ask that offline. But the other question is just more specific about a particular slide. When you were looking at finding maximum independent sets on K-tree embeddable graphs. And in the definition of a tree decomposition of a graph, you said that it had 3 qualities. One was an edge cover, one was a node cover, and one was the induced subtree property.
Right.
But I was wondering, in the case of finding maximum independent sets in say K-trees, don't you need some minimality of the as well? Because you could, for example, trivially extend a sort of a tree decomposition by repeating one of these clusters with exactly identical sets of nodes, in which case then that sort of recursive thing doesn't any longer hold.
No, no, actually it still holds. The only thing that happens is your running time will be worse because it depends on the size of the tree decomposition. So the running time of the algorithm, as long as it satisfies those properties, there's no problem with the algorithm. It's just that how long will you spend the running time of the algorithm depends on 2 to the k times the number of nodes in a tree decomposition. Now, if you are not minimal, then the number of nodes in the tree decomposition could be much larger than the number of nodes in the original graph. But if you take a minimal one, it won't be, it's basically going to be essentially linear in the size of the graph. So you don't want two adjacent bags which are basically the same. You can just collapse them and you'll be fine. So that will make sure that it doesn't, the size of the tree decomposition is not much bigger than the size of the graph. Yeah, that's, oh yeah, we shouldn't put redundancy in that.
Yeah. As an alternative to dynamic programming, what do you think of the work relating to minimum cost perfect matching for doing inference in planar graphs? And
the dynamic programming is sort of the standard way of doing algorithms on bounded Treewidth graphs, but inference is also done using belief propagation and stuff. I'm not an expert on some of these methods. There is a connection between doing dynamic programming and solving linear programming hierarchies in the Sharali-Adams hierarchy or Lasserre hierarchy and stuff. And one can show that in many cases that essentially this linear programming or semi-definite programming hierarchies are as powerful as dynamic programming. Now, instead of doing explicitly dynamic programming, you can try to solve those implicitly or explicitly, these hierarchies, and rounding algorithms for those can be interpreted as dynamic programming. So there is a connection between dynamic programming and these hierarchies, but these hierarchies allow you to do certain things without explicitly referring to dynamic programming, and sometimes they let you solve problems which are maybe more general than what the dynamic programming tells you that you can solve. So there are connections, but it's not sort of like a exact correspondence. So certain techniques which work, I mean, dynamic programming can be simulated by other algorithms too, right? So whether you want to think of it as dynamic programming or those other methods depends on the advantages of those other methods may offer you. Okay.
So this is your last chance to ask a public question. But there's many opportunities to ask private questions if you'd like to go up afterwards. So are there any other questions that anyone would like to ask? So if not, then let's again thank you for the excellent talk. It was very interesting. And this concludes the first tutorial session.